In this video, we used the molarity equation in combination with balanced chemical equations to carry out some very useful calculations for reactions in aqueous solutions. You may recall from an earlier video in this series that we were presented with this stoichiometric problem: the combustion of butane in the presence of oxygen to produce carbon dioxide and water. And we were given 5.78 grams of butane and asked to find the mass of carbon dioxide produced. And you recall that the way we tackled these particular problems was, in step 1, we first converted the mass of butane into the moles of butane. Step 2, we converted the moles of butane into the moles of carbon dioxide. And then in step 3, we converted the moles of carbon dioxide into the mass of carbon dioxide. And in both steps 1 and 3, we were using the molar mass equation. So we were going through this diagram in this U-shaped approach, going from step 1 through step 2 up to step 3. What I want to do now is just turn that diagram on its side. It's exactly the same diagram. We've got our U-shaped diagram, step 1, step 2 and step 3, now represented slightly differently. So if we were given the mass of substance A and we were asked to find the mass of substance B, we would still use the molar mass information to calculate the moles of A. Then we would calculate moles of B using the ratio of the stoichiometric coefficients, and then we would use molar mass information again to calculate the mass of B. Now that we've got our molarity expression and we are able to use information about the volume of a solution or its concentration, we can add to this diagram. So, for example, we might be given information about the volume and molarity of a substance A, and we might be asked to find the volume or molarity of substance B. So, in this case, we would still have to convert, now using the molarity expression, the information that we've got for substance A and calculate the moles of A. We then still need to calculate the moles of substance B using the ratio of the stoichiometric coefficients in the balanced chemical equation, and then we use molarity information again to find either the molarity or the volume of substance B. And so we would use this diagram going through step 1, step 2, step 3 in this manner. It could, however, be the case that we're given the mass of a substance A, and we might be asked to find the volume or molarity of another substance B. In this case, we would have to use this diagram in a Z shape, going step 1, mass of A, to moles of A, then convert the moles of A down to moles of B in the middle of this diagram, and then once we've got the moles of B, we can work out the volume or molarity of substance B across the bottom right-hand side of the diagram, step 1, step 2, step 3. It could also be that we're given the volume and molarity information of substance A, but asked to find the mass of another substance B. In this case, we would use this diagram in the S shape, going from volume and molarity of A, use the molarity information across the top, calculate the moles of A in step 1. Step 2, coming down the middle of the diagram, moles of A being converted to moles of B using the ratio of the stoichiometric coefficients in the balanced chemical equation, and then we convert the moles of B to mass of B using our molar mass information across the bottom left-hand side of that diagram. Whatever problem we're presented with in these solution stoichiometric calculations, there are always 3 steps involved, and we're always given information about one substance, A, and asked to find information about another substance, B. So step 1 would involve calculating the moles of A from the information that's given about substance A. Step 2 involves calculating the moles of B using the ratio of the stoichiometric coefficients from the balanced chemical equation. And then step 3, we would calculate whatever quantity of B we're asked to calculate from the moles of B determined in step 2. And so if we're asked to find mass, we would use the molar mass relationship, and if we're asked to find either molarity or volume, we would use the molarity equation to do that. So all of this is probably best described with a real practical example. So here's a typical question you might get along these lines. What volume of a 0.150 molar magnesium chloride solution is required to exactly react with 75.0 milliliters of a 0.12 molar silver nitrate solution? Now there's a lot of information in this question and we need to break it down. One of the first things we need is a balanced chemical equation. We actually have to identify what type of chemical reaction is going on here. Now we've got two solutions being mixed with each other, and this turns out to be a precipitation reaction. How do we know that? Well, we can do it almost by a process of elimination. We know that it's not an acid plus base. We know that it's not an acid plus carbonate. There's no acids present, there's no carbonates present. We know it's not acid plus sulfite. We know it's not an acid plus a sulfide. And we also know that it's not an acid plus a reactive metal. So almost by a process of elimination, we know that when these two solutions are mixed together, what we're talking about is a precipitation reaction. Precipitation reactions, remember, are double displacement or metathesis reactions, where we are going to swap anion and cation pairs. So the silver cation will displace the magnesium cation to produce silver chloride as one product, and the nitrate anion will displace the chloride anion to produce magnesium nitrate as another product. Before we attempt to balance this equation, we've got to make sure that the chemical formulas of these two products are correct. So is AgCl the correct chemical formula for silver chloride? Well, the silver ion is always 1 plus, it's a type 1 metal ion, and the chloride anion is always 1 minus. So these two things come together in a 1-to-1 ratio, and AgCl is the correct chemical formula for silver chloride. What about magnesium nitrate? Magnesium is a group 2 metal, Mg2 plus. Nitrate is a 1 minus polyatomic ion. In this case, when we do our crisscross, we're going to take the 2 from the 2 plus charge of the magnesium and make it the subscript for the nitrate ion. And we'll take the 1 from the charge on the nitrate and make it the subscript for the magnesium ion. And so the chemical formula for magnesium nitrate, after doing the crisscross method, MgNO3 So let's just correct that chemical formula there for magnesium nitrate. Now we need to balance the equation. We can see we've got 1 nitrate over here and we've got 2 nitrates over here. When we've got polyatomic ions on each side, let's balance them as a group and keep the polyatomic ions intact. You can see we've got 2 chlorides here and only 1 chloride on the right hand side. And in order to balance this equation here, if I put a big 2 out the front of the silver nitrate and a big 2 in front of the silver chloride, this equation is now balanced. We need to identify what subscripts we're going to put to these products produced, and silver chloride will form a solid precipitate in this particular example. Most chloride salts are soluble and would have the AQ subscript, but the big 3 exceptions being silver in this example and also lead and mercury. So we've got the S subscript there for silver chloride. All nitrate salts are soluble and will have the AQ subscript. So the magnesium nitrate will have that AQ subscript there. So already a lot of work done just to find the balanced chemical equation. What it's useful to do now is to write down the information that we've been given about each reactant and the information we've been asked to find. So we've been given the fact that it's 75 mils of 0.12 molar silver nitrate. And we've also been given information about magnesium chloride, and the concentration of the magnesium chloride solution is 0.15 molar. And all of that information there about silver nitrate is given in the question. 75 mils, 0.12 molar silver nitrate. So it's important we break down this question and work out what it is, what's the information we've been given about each reactant. And the 0.15 molar magnesium chloride information given there. Been asked to find the volume of magnesium chloride. So that's the essence of this question. What volume of magnesium chloride is required to exactly react with 75 mils of 0.12 molar silver nitrate solution? So we would go to a diagram like this, and what's relevant here is just the right-hand side of this diagram. We've been given information of volume and molarity about silver nitrate, and we've been asked to find information about magnesium chloride. Specifically, we've been asked to find the volume. So we're going to start with this information up here, the volume and molarity information for silver nitrate. We're going to use our molarity information to calculate the moles of silver nitrate. We'll then calculate the moles of magnesium chloride that's required to exactly react with those number of moles by using the ratio of the stoichiometric coefficient. So that'll be step 2. And then finally, step 3, we will use molarity information here to find the volume of magnesium chloride. So we're going step 1, step 2, step 3 in this fashion here. So, step 1, moles of silver nitrate equals molarity of silver nitrate times the litres of silver nitrate. Now you recall that the molarity expression is molarity equals moles on litres, and we can make moles the subject of the equation. Moles equals molarity times litres. So that's the expression we're using here. We substitute these two values in with the 0.1 molar is what's been given in terms of the molarity of silver nitrate, and we've been given 75 mils of silver nitrate, and we convert that into litres, 0.0750 litres of silver nitrate. Plug that into our calculator and we get 9.00 by 10 to the minus 3 moles of silver nitrate. Step 2, we need to convert the moles of silver nitrate into the moles of magnesium chloride. So the moles of magnesium chloride will equal a half times the moles of silver nitrate. And that half expression comes from the ratio of the stoichiometric coefficients. So we've got the 1 in front of the magnesium divided by the 2 in front of the silver. So it's the ratio of the stoichiometric coefficients, the stoichiometric coefficient of the substance you've been asked to find information about, divided by the stoichiometric coefficient of the substance you've been given information about. So a half times the moles of silver nitrate equals a half times the 9.00 by 10 to the minus 3. We calculated that in step 1, and when we plug that into our calculator, 4.50 by 10 to the minus 3 moles of magnesium chloride. So finally in step 3, we want to calculate the volume of magnesium chloride. So how many litres of magnesium chloride? Litres equals moles over molarity. We're being asked to find the volume, and you'll recall that the molarity expression, molarity equals moles over litres, so we can make the volume or litres the subject of that equation by saying that litres equals moles over molarity, and that's the expression we're using here. So the moles of magnesium chloride, 4.50 by 10 to the minus 3, we calculated that just in step 2 a moment ago, and the molarity was given to us in the question, 0.15 molar. When we put that into our calculator, we get 0.0300 litres, and we can convert that to millilitres if required, 30 millilitres of magnesium chloride. So in summary, the answer to this question is that it takes 30.0 millilitres of 0.150 molar magnesium chloride to react exactly with 75 millilitres of 0.12 molar silver nitrate.